Can you hear me? Thank you for that very kind introduction. I have almost no time left for my presentation. It's a great honor and a privilege indeed to talk to you today about some ideas, some concepts that are perhaps a little bit new. Systems thinking in chemistry education, and also the molecular basis of sustainability. And to be able to do so at the Mendeleev Congress here in St. Petersburg, and to do so in the middle of the International Year of the Periodic Table, for which Mendeleev played such an important role. One of the wonderful things about coming back to Russia for a conference is to meet old friends again and to make new friends. And I met an old friend who you will recognize, and I learned the vodka in St. Petersburg is a little different color than the vodka in Moscow and Tobolsk, where I've been before. But also making new friends. And I think, if I was counting right, this is the 118th new friend I've made at this conference, academician Oganessian. And what he's showing me here is Mendeleev's Chemical Principles, the third edition. And so my talk is focused on chemistry education, and it's a real privilege to be able to do so in St. Petersburg, where Mendeleev did so much of his work. And so much of his work was focused, of course, also on chemistry education. So what I'd like to do to organize my presentation today is to start with a project of UEPAC. You've heard about UEPAC from Javier. A project on systems thinking in chemistry education. And from there to introduce the idea of the molecular basis of sustainability, which we would like to become a core outcome for chemistry education. And then introduce some tools to think about systems thinking for educators to be able to use systems thinking. And the example I'll use will be a very familiar one after Javier's lecture. Finally, to talk about the next steps for systems thinking in chemistry education, which I'm abbreviating STICE. Chemists have learned well how to fractionate. You heard this also from Javier. In fact, Mendeleev traveled to Caucasus, to the beginnings of the oil industry, where we've learned a great deal how to take carbon atoms that are stored in the ground for geological time and to transform modern life through the combustion of fossil fuels. Chemists have learned how to do this very well. Can chemists also play a central role in solving the unintended transformations of all of those hydrocarbons? And I show you here the Keeling curve and going back to before the Industrial Revolution. We heard in a wonderful lecture yesterday from our colleague from Leiden that the oxygen-hydrogen bonds in water molecules typically are perhaps 4.5 billion years old. By contrast, if you look at carbon dioxide molecules, many of the carbon dioxide molecules in our atmosphere now have had their carbon-oxygen bonds formed during our lifetimes because of the scale at which we've been combusting hydrocarbons. And so understanding those cycles of carbon are very, very important. And to illustrate this, I'd like to show you a portion of a simulation we're working on at the Center for Visualization in Science, which I direct, kcvs.ca. And the focus of this simulation, which will be released publicly in about 2 weeks, is to help us understand how we can mitigate the greenhouse gases found in our atmosphere. So on the y-axis is the amount of carbon dioxide equivalents per year that human beings are producing. And we go back to the Industrial Revolution, and I've placed on that graph Mendeleev and the discovery of the periodic table. And you can see at the time of the discovery of the periodic table, the contribution of human activity to greenhouse gases, to changing the radiation balance of our planet, was very, very small. Nature had the capacity to assimilate those carbon dioxide molecules. But now, only 150 years later, as we celebrate the 150th anniversary of Mendeleev's periodic table, we're now producing almost 40 gigatons of carbon dioxide equivalents per year. And I'd like you to think with me for a moment as we look back on the wonderful celebration of the last 150 years. I'd like you to think with me about the future. So perhaps in St. Petersburg, in another 150 years, a group of chemists, none of us included, will be gathered to celebrate 300 years since Mendeleev's periodic table. But what will the concentration of greenhouse gas equivalents be in 300 years? This is the trajectory that we're on as human beings. And what role will chemists have to play in taking all of the little incremental steps? There is no silver bullet, but perhaps there is silver buckshot, if you understand that term. Many things that we can do, and you've heard some of them today from Javier and from our earlier speakers, to bring down the concentration of carbon dioxide and other greenhouse gases in our atmosphere. So chemists are very good at fractionating, but maybe have yet to really take on the task of the systems that have resulted from all of that combustion of fossil fuels. And now let's turn to chemistry education. I think chemistry educators are also very good. They're experts at fractionating. There's a quote by Joseph Bordogna, who was a former director of the National Science Foundation in the United States. And he talks about the importance of specialization in our world, in science education. We must have specialized knowledge. But in the process of teaching students all of that specialized knowledge, he uses the metaphor of fractionating. We continually fractionate knowledge, make it more and more specialized. And Bordogna asked the question, what other skills will be needed? And this was written in 1991, in the 21st century, for students to be able to look to the future. And so my suggestion today is that one of the ways to move beyond fractionated knowledge in chemistry education is to use tools that have become important in other disciplines but are largely unknown in chemistry and chemistry education, and those are tools of systems thinking. So what do we mean by systems thinking? We use tools, strategies, and cognitive frameworks, our understanding of how students learn, to visualize interconnections and relationships among components of complex and dynamic systems. We examine how behavior of systems changes over time. And maybe, perhaps even most importantly, one of the things that happens when we look at systems is we see that systems have behavior that can emerge, that's greater than the sum of all of the parts. And so about 1.5 years ago, we founded a project called the UEPAC Systems Thinking and Chemistry Education Project, which we call the STICE project for short. And it's with the motivation of applying systems thinking to chemistry education and to understanding how that can help the next generation address emerging global challenges.